All right, so let's start with section 2.2 right at the beginning of Calc 2. We are going to do determining volumes by slicing. So we'll start off with the definition. We're going to talk about the cross-section of a three-dimensional solid. So think of it as just some three-dimensional object, maybe a loaf of bread or something that you have on your desk. And if you were to take a piece of paper and slice it right through from the top to the bottom, just like you see right here in that image, that's called a cross section. The shape that that piece of paper makes with the solid is what the two-dimensional cross section looks like. So in this case, that semicircle is the shape that that piece of paper makes when it slices this object right from the top to the bottom. So what we're going to do is we're going to try to find the volume of that three-dimensional object. That's the goal there. So what we're going to do is we're going to take that slice that we have and do a whole bunch of slices. All right, we're going to keep slicing across that entire three-dimensional solid. And in this example that you see, each one of those cross sections has a semicircular two-dimensional shape. What we're going to do is take each one of them and add them all up to get a total volume. So add up the volume of each one of those little slivers. So that's what this is saying here. To find the volume of a solid, we're going to break the solid up into smaller cross-sectional pieces and then estimate their volumes. And it could be an estimate because it's not always going to be a perfectly shaped semicircle or a perfectly shaped cylinder. So they might be estimates. And then we're going to add up those volumes to estimate the total volume of the solid. So a really good way, this next visual, is to think of taking a solid and slicing it up like it is an actual loaf of bread. So you see that first image here, if I were to slice that up, and each of those slices actually have a little thickness to them. Okay, and so once they have a little thickness to them, that's actually a three-dimensional sliver or slice of bread. So it's not a two-dimensional cross-section. But then what I do is I can take that little thickness that each of those pieces have and make them smaller, and then even smaller. And then you can see that the more you do, the better it's going to be at creating that entire three-dimensional solid. So it's just like it was at the end of Calc 1. You're going to add up infinitely many rectangles like you did in Riemann sums. Only in this case, they're not rectangles, they are cross-sectional pieces to find the volume. So still the exact same thing. And so then to find the volume of that solid, that's what we're going to do, break it up into smaller pieces, and then we're going to eventually take that limit and do infinitely many. So take that limit and do infinitely many. Suppose a solid object extends from x equals a to x equals b. What that means right there is we're just trying to take the x equals a and x equals b is the beginning and ending of that loaf of bread. And then a cross section perpendicular to that has, let's say, an area given by A. We're just going to use capital A for area. We're going to use capital V for volume. And then what I'm going to do is add up all of those pieces. So that infinitely many really was going to be the integral, just like it was from Riemann sum. So this is kind of hard to see. Maybe I can zoom in so you can see that a little bit better. That volume really was the limit as n goes to infinity of the sum of each one of those areas times the thickness of that slice of bread. And just like in Riemann sums, that turned into a definite integral. So now we have this sort of main formula for this section so far here on page 1. The volume is the integral of the area function. And it might be dy depending upon how you've drawn the picture. We're going to come back to that. So I've got some strategies for us that can help us by finding the volumes. This is called the slicing method. There's more than one method that we're going to learn. We're just starting off with the first one. The slicing method, you really should be thinking of it like a loaf of bread. So step 1 is to draw a picture. Always, always, always. This is going to be very visual. The picture is going to be not just so you can visualize maybe what's going to be on top, what's going to be the bigger volume, things like that, but it'll also help you identify whether or not you're going to need a dx or a dy in your integral. So the picture is going to be really important. You're going to first sketch a graph of the base of the solid. That's the two-dimensional bottom of your solid. So like that's the bottom of your loaf of bread, the thing that's touching the cutting board. All right, that's what it is right there. Try to visualize the solid and determine the shape of the cross-section of the solid. This one, I think that middle step there, honestly, that one's a little bit harder to draw in 3 dimensions. So try to visualize it. It's okay if you can't draw that one. But the most important part of drawing is the two-dimensional part, the bottom, the part of the loaf of bread that's touching the cutting board. The other one, you might have to visualize it in your head. We're going to try to define a formula for the area of that cross section. And then just like that formula we had above, we're going to integrate the area formula to find the volume. Okay. All right. So in general, the volume is equal to the integral of the area function. All right, let's do an example. I'm just going to kind of draw a picture here right from the beginning, and we'll see if we can visualize this in 3 dimensions after. So I'm going to wait a second to visualize it. Let's just read through it and draw a picture from the beginning. Use the general slicing method to find the volume of the solid whose base is on the xy plane, bounded by y equals x squared and y equals x, and whose cross sections perpendicular to the base and parallel to the y-axis are squares. All right, step 1. Every single time is going to be to draw a picture. Now, your picture doesn't have to be perfect, and it probably isn't going to be 3 dimensions to begin with. What we're going to do when I say draw a picture, I really mean draw the cutting board. This is the 2-dimensional, just the bottom part of your solid that's touching the desk or your cutting board, right? So in this case, it even tells me the base. This is what I'm drawing. I'm drawing the base. The base is on the xy plane. So I've drawn the xy plane, and it's bounded by, I've got y equals x squared. We can graph that, pretend I'm a good artist. There's my y equals x squared. And I also have y equals x, so I'm going to graph that as well. I'm going to try to label as much as I can. And then I'm going to shade in the region bounded by those 2 graphs. So this is the base of my solid. And then this is the part that's going to be a little bit harder to visualize. I'm not going to be able to draw it in 3 dimensions, but we're going to try to think about what's happening here. This is the bottom. So this is your cutting board, the thing that's on your desk in front of you. And then popping out of the screen at you are going to be cross sections. So when I say perpendicular to the base, that just means directly out of the screen at you, right? So that really is going to be the screen is your cutting board, and the piece of paper or the knife that we're using to slice this loaf of bread is going to be perpendicular to that cutting board. All right, and then they're also going to be parallel to the y-axis. So that parallel to the y-axis just means that my slivers, I'm going to maybe zoom in here a little bit, are going to be like this. I'm going to slice through my object like that, rather than, because I could have chosen to slice parallel to the x-axis, but I just chose to slice parallel to the y-axis, because that's what it says there in the problem. Okay, and those are all squares. So like I said, it's going to be hard to imagine, but you got to imagine that those are squares, and they're not sideways like that. They're actually popping out of the screen at you. That's what they are. They are popping out of the screen at you. And so each one of those squares, we're going to try to find the area of the squares. So the first thing that I recommend that you do is to find the area of the cross section. Okay, and then we'll find the volume later. So to find the area, I'm going to use just A for area. First, think about it in words. The area of a square is really simply as easy as it is. It's the side length times the side length. That's the area of a square. So I'm going to write it in English first and then try to translate it a little bit more into math. So in this case, each one of these squares are going to be popping out of the screen at me. And each one of them is going to have this little sliver be one of the side lengths. And each one of those side lengths looks like they are a y value, right? So it really is going to be a y value or a distance in the y direction, right? So it's going to be, maybe I'll write it like that, as a distance in the y direction is what the side length is. Okay, so then in this case, that distance in the y direction was just going to be the top minus bottom. It really is going to be that first one was the y equals x, and then the bottom one was y equals x squared. So that really is the x minus the x squared. All right, that's what it is that we're thinking about right here. So now I've taken my area of a cross section. I thought it through first in English, compared it to my picture, and then actually had a formula. So that's pretty good that I have so far. Then I have to do a simplification here. So I'm going to choose to simplify it right away. I'm actually going to FOIL it. And I'll show the work just here at the beginning, but this is stuff that you might be able to eventually hopefully do in your head. If you need to show all of the work, that's still fine. But good old-fashioned foiling. So I have an x squared minus an x cubed minus an x cubed plus an x to the fourth, which is x squared minus 2x cubed plus x to the fourth. All right, so now I have all of that. So then from here, I'm going to kind of change the color, and I'm going to do a little arrow over here. That was the area of the cross section. So now I want to find the volume of the solid. So the volume is always going to be the last thing that you do. The calculus will be the last thing that you do. And it's the integral of that area function that we just found. So that's what it is that I'm doing. And my bounds are going to be from 0 to 1. And I'm going to point this out really quick. Your bounds are going to come from the picture. The picture is so important. I had a dx here. So I'm going from 0 to, and you can just see where those two intersect. It's from 1. If you're not sure where the two graphs intersect, you would set them equal to each other and then solve. Oh, sorry, that was x squared equals x. There we go. You would set them equal to each other and then solve. All right, but there we have it. Okay, so I got my integral there. Then I just have to go through and calculate. So this is the integral from, oh, I don't need to simplify. It's already simplified, sorry. I'll do the antiderivative. So I add 1 to the power, divide by the new power, add 1 to the power, divide by the new power. I'm just doing the power rule for integration here for each one of those. And then I'll plug in my bounds. We can do it. I got 1/3 minus 2 over 4 plus 1 over 5 minus, if I plugged in 0, it just so happened to be 0 everywhere. Of course, that won't always be the case, but there it is. So then my answer was 1/3 minus 1/2 plus 1/5. And of course, you can use your calculator, and I'm going to show you guys really quick a nice little trick if you don't already know this in your calculator. Let's see if I can get my calculator to open up, potentially. There we go. Sorry. Okay. All right. So that's what it is that I'm looking at right there. So if I wanted to do it was 1/3 minus 1/2 plus 1/5. Let's say I wanted an exact answer. So I'd always like to have an exact answer unless the question needs a decimal rounded to something. So there's a button there on the top left, right underneath the green that says math. So before I click enter, I'll click math first and select the fraction button. And then it just combines that for me as 1 over 30. So then I have the final answer of 1 over 30. Ta-da! All right, so that's what we got there for the general slicing method. I did want to show you a nice visual of that at least, so you can see maybe what that might look like in 3 dimensions. GeoGebra is a really good tool that you might find helpful in this class, especially when you're trying to visualize what's happening along the way. So here's an example. There's that base that we had on the left. That's the base. That's just sort of the thing that's touching the cutting board. And then there it is, the 3 dimensions on the side. And I'm going to show you what those squares might look like. So you can see how there's a bunch of squares sort of popping out of the cutting board, but still the base is bounded by those 2 graphs. So then you can sort of see maybe, there we go, there's a few more of those squares, and then a few more, and then a few more, and we kind of added up all of them. That's what the integral was. And so that was the 3-dimensional solid that we found the volume of. Kind of helps you visualize that a little bit more. Maybe the less squares might make it a little bit more visual as well. Cool. All right, so let's go back to it. So that's the general slicing method. Let's practice another one. So same idea, but maybe without a visual in 3 dimensions. Let's see if we can just come up with this one as it is. And so find the volume of the solid whose base is the triangle made from these vertices. So I'm going to start off with the base. We're going to start off by drawing a picture. And in this case, the base is, it looks like a triangle bounded by these vertices right here. Pretend I'm a good artist. It's probably not to scale, but it's maybe close enough. So here is the base. So that's, again, this is like your cutting board. You have to imagine a 3-dimensional object popping out of the screen at you. That's my base. And then I'm going to think about the cross sections. This one's that's maybe a little bit harder to draw. You might be able to draw it really well if you're an artist, but it's probably a little bit harder to draw. So we have to try to visualize it in our head. The cross sections are perpendicular to the base. When I say perpendicular to the base, I just mean popping out of the screen at you, and then parallel to the y-axis. So each one of those slices are parallel to the y-axis. And each one of those are going to be popping out as semicircles. So you have to imagine that that was sort of popping out of the screen at you. I'm not a great artist, so I'm going to ignore that drawing. And those are semicircles. So then the next thing we want to do is we want to find the area of the cross sections. You find the area first, and then you find the volume. So I'll use A for area. So the area of a semicircle. Well, there's not even a picture. It's not 1/2 base times height. There's not a triangle in here. I know it feels like there is, but that's just the base. The cross sections are not triangles. Those cross sections are actually semicircles. That's what you're finding the area of. And the area of a circle is pi r squared. So the area of a semicircle is 1/2 pi r squared. And so then I'm going to do a little bit more thinking about what the radius is. One more time, you have to visualize those circles that are popping out at you like this. Those are those semicircles. So each of those little white slices that you see in my picture are actually the diameter, because that's all the way across, right? So the radius would be half of each of those distances. So the radius is not the full y value, it's only 1/2, of the y value. It's only 1/2 of that y value. So that one's a little bit trickier to think about, but I think we can come up with that there. So it's 1/2 the y value. I'm going to actually come up with what the y value is. So I have the 1/2. I'm going to leave a little blank there. I want to figure out what the y value is. In this case, I didn't have an equation. The last one I had an equation here. I have to find the equation of that line. So the equation of that line, maybe I'll use a different color so you can be real clear. That's the line I'm looking for to find the equation of a line. It's y equals mx plus b, where the slope is rise over run. You might be able to visualize that rise over run. It looks like it went down 8 and over 8. So that was a -8 over 8, which is just 1, x, plus the y-intercept is 8. So I had a y equals -x plus 8. So that's that y value. So that's what's going to go right here as that -x plus 8 for that y value. And then I'm going to simplify it along the way. I'm going to skip the algebra there, but make sure you know how to do that algebra. I'm going to actually simplify this. You know what, actually, maybe instead of foiling it, I'll show you a little trick here instead. So I'm still going to simplify that. That's 1/8 pi times -x plus 8 squared. I'll point out where that came from. The 1/2 squared is 1/4, and then times another 1/2. That's where that 1/8 came from. Now, you could FOIL it, by the way, you can. If that was your habit, it would still work, I assure you. I just want to show you something kind of neat here. So my next step was to find the volume, which is going to be the integral of that area function. So -x plus 8 squared dx, okay? And then my bounds were from 0 to 8, and that came from the picture from 0 to 8. Those are the x values that I had from my picture of the base of this three-dimensional object. And then maybe remember from Calc 1 that because 1/8 pi is a constant multiple, it can be on the outside of that integral. Sometimes that makes the integration a little bit easier, so I'll leave it there. And then there's a nice little trick that we can think about for integrating when you have the inside, I'm thinking of this inside right here, be linear. You can do a u-sub. You can let your u be that inside. I encourage you to maybe pause the video and try the u-sub. Okay, now you've tried the u-sub, here's the nice trick, and it only works because the inside was linear. When the inside is linear, what I could do is just do the antiderivative, the whole add 1 to the power, divide by the new power. You just need to also divide by the constant multiple. So in this case, that constant multiple was a -1, so I had to also divide by that -1. Evaluated from 0 to 8. And then I'll plug in my bounds, and so that gives me 1/8 pi times, if I plugged in 8, I got -8 plus 8 cubed over -3 minus 1/8 pi. If I plug in 0, I got -0 plus 8 cubed over -3. And then you can use your calculator to simplify that along the way, and I hope you're able to. I ended up with 64 thirds. There we go, pi. Sorry, I had to think about that. Feel free to use your calculator to double check. I still had a pi involved. This guy went to 0, and then an 8 cubed times the 1/8 was an 8 squared. And those two negatives did cancel. It should be that you have a positive value because you found a volume. So a volume should definitely be positive, not negative. Ta-da! Cool. All right, let's try to do another one. Let's see how far we can get. I'm not going to be able to do all of these examples. There's going to be a ton of examples that I want you guys to practice on your own. There's plenty here for you to practice on your own. And if you've got questions, you can let me know. But let's practice one more. Let's practice one more of the slicing method. All right, so if a pyramid has a square base with the length of one side of the base is 2, and I just called it A, so you can see in my picture that that's what this A here was. So A was 2. And the height of the pyramid is h equals 4. So again, that's just what I called that height there. Use the slicing method to find the formula for the volume of the pyramid. And I'm not sure I should have used the word formula there. We're just going to find simply the volume, okay, of the pyramid. That's what we're going to do. So you should be able to see from this picture that in this case, my slices are like this. And each one of those slices, if you look real carefully at that three-dimensional picture, are perfect squares. Okay, so just like we've done before, the first thing you do is find the area of, well, I should say the first thing that you do is draw the picture. The picture's already drawn for us. The area of the cross section. Okay, each of my cross sections in this case are squares, and the area of a square is the side length squared. Okay, and my side length is, if you look at my picture, it was this guy, that big square right there, the side length would be this guy. And then you should notice over here on the left that it's going to be a smaller square eventually, right? And so then that side length would be different. So each one of these slices that I'm doing right here on the right-hand side of those pictures, you're seeing those slices, each one of those slices, right? The side of the square is going to be from the top to the bottom, which in this case is twice the y value. Because you should see that the y value just went from the x-axis to the top of that pyramid. And then I needed twice of it though, because that square goes to the top and bottom, so above and below the x-axis. So it's actually twice the y value. So let's write that down in English. Sometimes if you write it down in English first, it's a lot easier to do the math. Notice that the calculus is always like the last thing that you're doing when you're finding the volumes. That's the easy part. You do that one later. You set up everything first. All the setup is going to come first. So twice the y value. All right, so I got to find the y value. So just like I did before, I'm going to find the equation of that line. So how do I find the equation of that line? Well, it's y equals mx plus b, just like we did before. And then in this case, it went up. Let's see, it said it had a height of, it looks like it went up 1 because it said a was 2. I'll scroll back in case you don't have that in front of you. It said a was 2. So when I do the slope here, it looks like it went up half of that, which is 1. And then it went over all the way h. And in my case, h was 4. So it went up 1 over 4. And it had a y-intercept of 0 because it touched the origin right there. So I ended up with y equals 1/4 x. All right, so that's what I can kind of plug into here to find that area of the cross section. So now I have that my area is twice the y value and then squared. Okay, and then I can simplify that. 2 times 1/4, of course, is just 1/2. And then 1/2 squared is 1/4, and x squared is x squared. So there's my area. So then last but not least, you do the calculus. And so the volume is going to be the integral of that area function. And you go back and look at your picture and you should see that the bounds in this case would be from 0 to 4. Going back to look at my picture, it went from 0 to the x value of 4 because h was 4 in my example. And then I'm going to go through and calculate that. I'm going to go over here to the side. It looks like I have 1/4 is a constant multiple, so it stays x cubed over 3, evaluated from 0 to 4. I can plug in 4, and then I can plug in 0 and subtract them. Use your calculator if you need, but make sure you leave it as an exact answer. Don't round unless the question asks you for a decimal. And I'll go ahead and put units cubed just to remind you that we did in fact find a volume. If it were an area, that would be units squared. Ta-da! Awesome. All right, so that was the slicing method. Now let's move on to another method of finding a volume. Okay, so we're still finding volumes. All of section 2.2 is all going to be about volumes. So we still are finding a whole bunch of volumes. So the first one is if a solid of revolution is the definition of what it is that we're trying to find. We're revolving an object around something. If a region in a plane is revolved around a line, then the resulting solid, this is a solid, so it's filled in, is going to be called a solid of revolution. We're going to use the slicing method to find, which is the method we just did, to find the volume of that solid of revolution. And in this case, though, because it's a revolution, so I'm taking this entire object and revolving it all the way around, it creates a circle just by the nature of revolution. All right, just by the nature of revolution. So it creates a circle. So that's why the cross sections are circular, and the area of a circle is pi r squared. Always has been, right? The area of a circle is pi r squared. So because I'm creating a circular cross section, the area will be pi times the radius squared. And in this case, the radius is going to be just that y value, because the diameter would have been twice the y value there. All right, and then I'm going to find the volume, and the volume will be still the integral of the area, which is why I now have that volume is the integral of pi times the radius squared. It might end up being dy, depending upon your cross sections, and it'll all come from the picture. So the big thing that you're going to want to focus on is the picture here. All right, so let's go ahead and do that. Each cross-sectional piece will be a disk or a circle of radius, the y value, which is just f of x. The area of a circle is pi r squared. So now we know what our volume is going to be. Let's do an example. All right, I'm going to visualize this example first. So what I'm going to do is read it out. I've got R is the region bounded by this curve, the x-axis, and the lines x equals 0, x equals 2. I want to find the volume of a solid of revolution obtained when I revolve this object completely around the x-axis. All right, let's see if we can visualize what that might look like here. CalcPlot 3D is another great website to help you visualize three-dimensional objects, especially in this class. There's going to be a whole lot of visualizing. It's easy to play around with it. This is just I'm just touching it from my iPad. This is the iPad touchscreen here, but you might be able to use that with a mouse as well on your laptop if you need. But you could then just move this around to visualize things in 3 dimensions. So here's the object, and I'm going to revolve this entirely around the x-axis. And then you should be able to then see how that created a 3-dimensional object. Kind of looks like a flying saucer. That's the volume that we're trying to create here. All right, so I revolved that entire region. I could also just revolve that one rectangle to help you visualize the circle that happened. Right, I just took one little sliver or cross section and revolved that around the x-axis. And if I did that for all of them, you're going to end up with this 3-dimensional solid. That's what we are trying to find the volume of. Okay, let's go through and do it. So step 1, no matter what, is to draw a picture. Now, you might not draw it in 3 dimensions. You probably don't need to draw it in 3 dimensions. You do need to visualize it, at least in your head, in 3 dimensions. But draw the 2-dimensional part first, and then we'll start revolving later. So I am going to draw my function, which is x plus 1 squared. So I'll graph that y equals x plus 1 squared. Feel free to use your graphing calculator if you'd like, but hopefully we know that shape here is, I'm going to call it f of x just because that's what this question called it. If you called it y equals, that would be fine. That's the shape of that graph. And it looks like I'm going, and the x-axis and the lines x equals 0. Oh, I'm sorry, I drew the graph wrong. I should use my graphing calculator. Let me try that again. Sorry about that. Y equals x plus 1 squared is shifted over here. Sorry about that. There it is. That's my f of x. That's a little bit better at least. And then I'm going between the x-axis, this function, and x equals 0 and x equals 2. So here is the shaded region in question. You should always shade in the region. Your life will be a little bit easier there. And then I'm going to pick that object up, and I'm going to revolve this around the x-axis. So I'm going to draw a little sliver here. I'm going to zoom in a little bit to try to make that more visual for you. I'm going to draw one single little sliver here. I'm kind of being dramatic about my sliver because that'll help me visualize it here. And I'm going to take that sliver and I'm going to revolve it around the x-axis. Hopefully you can then see that circle. All right, and so what I've done is I've revolved it all the way around, and I would do the same thing with each one of these slivers. But you can see how if I revolved this one around, it would be a slightly smaller circle. And if I revolved this one at the very end, it would be an even larger circle. So hopefully you can start to see that this is in fact that flying saucer that I'm creating. And this is what we're trying to find the volume of. Okay, it's not super easy to visualize, I know, but we can do it. So here it is. Volume is going to be, you can see each one of those cross sections was a circle. So the area of a circle is pi times the radius squared. All right, my bounds are going to go from 0 to 2. Looking at that picture, if you look back at your picture, I'm going to erase the stuff I've got in the way here. And if you look back at that picture, the original picture that I had, there we go. Okay. You should be able to see that all of that shaded region, each one of those slivers went between 0 and 2. So that's where my bounds went from 0 to 2. And then it's the pi times the radius squared, and each one of those circles that I erased because I didn't think I had a good picture there, but you can still keep visualizing them in your head, had a radius of the y value. Each one of those circles had a radius of the y value. And in this case, my y value is x plus 1 squared. All right, and so that's going to become the integral. Simplify along the way. Keep track of your equal signs. Make sure they're clear. Make sure you know what it is that you're calculating. Make sure every equal sign is still a true equal sign. X plus 1 squared becomes x plus 1 to the 4th. And then pi is a constant multiple. It can stay. Then I can do the calculus. So it's linear on the inside, so I can still add 1 to the power, divide by the new power, so long as I also divide by the constant multiple. And in this case, that constant multiple is the slope of the linear thing that's on the inside, just on the inside, which in this case was just a 1. So that's why there's an extra 1 on the bottom. And then I evaluate that from 0 to 2. And then we're going to do the same thing. Right now I'm evaluating that guy from 0 to 2. Yeah, there we go. So I could plug in. Yeah, there we go. I could plug in, sorry about that. I could plug in x equals 2 and then x equals 0. If I plugged in 2, I would get pi times 3 to the power of 5 over 5 minus pi times, if I plug in 0, it looks like I got 1 to the power of 5 over 5. And I'll use my calculator, and I got 242 pi over 5. And I'll go ahead and circle that answer, or you could write units cubed to remind you that you found a volume. Ta-da! All right, so we have now what's called the disk method. So that's the disk method, which is pretty good, not bad. We have another method. Let's do some more practice of this one before we do one more method. All right, so I'll practice one more for this one. Find the volume of the solid created when the region bounded by the graphs of this function, x squared plus x minus 2, x equals 2, x equals 4, and y equals 0 is rotated about the x-axis. Let me draw the picture first, and then I'll help you guys by visualizing it in 3 dimensions. So the picture that I'm going to draw is first f of x equals x squared plus x minus 2. Now you can use your graphing calculator. You really, really can. You might, however, get used to, and you'll start to recognize some helpfulness behind this too, is if it can factor, it might be more visual to graph, especially when this turns into something where I might have to use a dy. So it doesn't always though, so this might not always be helpful, but it might be. So in this case, it does factor as an x plus 2 and an x minus 1. The reason why that's helpful is then I have my negative 2 and 1 as the x-intercepts for that parabola. Like I said, maybe you choose to use your graphing calculator instead, but it's worthwhile to have some tricks up your sleeve. All right, so I've graphed that function. I have a few other ones. I also have x equals 2 and x equals 4. So here's my x equals a number is a vertical line. So here's your x equals 2, x equals 4. I also have y equals 0, and y equals 0 just is the x-axis. So then you should be able to see here is my shaded region. And this is the thing that I'm going to pick up and revolve around the x-axis. So I like to draw that little arrow to help me visualize it. I'm going to draw my sliver again. There's technically infinitely many slivers that we have. Here's one of these little slivers right here. And I'm going to revolve that around the x-axis. You should be able to see the circle that that creates, or the disk that that creates. So this is the disk method that I'm doing. I'm going to erase that circle. You can keep that circle there if that's more visual for you. And then each one of those little slivers, remember there's technically infinitely many of those slivers. You should see that all of those, if I were to zoom in, have a small little width of delta x. So that means that my integral is definitely going to be a dx. So maybe a little side note, if your sliver was drawn this way, then that would have been a dy. And we'll have some examples of that later, but a good little side note. So then the area of that circle is pi times the radius squared. My x values were from 2 to 4, and the radius is that function, which is just x squared plus x minus 2. All right, so that's what we've got so far, and I'll go through and set that up for us. So this is going to become, I'm going to take the pi on the outside because that's a constant multiple. It can just stay. And then you really would have to FOIL that. Because it's not linear on the inside, you can't do that trick like we did for the other ones. You really would have to go through and FOIL that completely before you did the integral, which means I had to keep that integral notation there to make sure that everything is written correctly. And if I were to FOIL that, I would get x to the fourth plus 2x cubed minus 3x squared minus 4x plus 4. I skipped some steps there, so feel free to pause the video and see if you can end up in the exact same spot as this, and then do the antiderivative from there. So I would add 1 to the power, divide by the new power, etc., etc., etc. You guys should be able to do that antiderivative, plug in your bounds from 2 to 4, and I ended up with 1232 pi fifths units cubed. I just used my calculator to type that in, use the fraction button. Hopefully I typed it in correctly. Ta-da! All right, we're doing good. So far, that's what we've got is the disk method of finding the volume of revolution. So that's looking really good. I'm going to skip this example 6. I want you guys to try that one on your own. See if you can come up with an answer for that one. I think it'll be really useful to be able to come up with that on your own. I can tell you that the answer I got for that one was 3 pi over 4 as the final answer. So you could use that as a way to check your work. Try that one on your own. But I'm going to skip a couple other ones as well. I'm actually going to skip, there's plenty that here for you to practice, but I'm going to skip to example 8. This one is going to be a little bit more useful for us. So let's say R is the region bounded by y equals 4 minus x squared, x equals 0, and y equals 0. So the first thing that I do is draw a picture. 4 minus x squared, we know looks like this. Here is my y equals 4 minus x squared. I also have x equals 0, y equals 0 in the first quadrant. So x equals 0 is the y-axis. Let me say that again. X equals 0 is the y-axis, and y equals 0 is the x-axis. So then you should be able to see that in the first quadrant, this is that region in question. I still think it's worthwhile to shade in the region. I find that the most beneficial to visualize where your slices are going to be, because you have to remember that there are infinitely many slices here. So I'm going to try to draw my slices. I'm revolving this about the y-axis. So in this case, if I were to revolve it around the x-axis, my slices would look like this, and I would revolve around the x-axis. But in this case, I'm revolving around the y-axis. So to use the disk method, revolving around the y-axis, I would have to draw a horizontal sliver. So that way I can revolve that around the y-axis, and hopefully you see now that disk or circle on its side. So here's that disk on its side. And of course, there would be other ones up here as well when I did that revolving. And you can see that each one of those horizontal cross sections now are still circles because I'm still doing the revolution. It's just now on its side. And when it's on its side, you've got all infinitely many of those slivers. Each one of those slivers or slices are going to have a small little width of delta y. So in this case, my volume, let's see if I can get that written up. Here you go. My volume is now going to have a dy. You still have a pi r squared because the area of a circle is still pi r squared. That part isn't changed. The area of the circle that I just created when I did that revolution is still pi r squared. All right, but now it's a dy, and then I'm going to look at this picture over here, and I'm going to notice that with that circle that I did that revolution of, that circle has a radius of an x value. So now that radius is an x value. So I have to rewrite my equation to be in terms of an x equals instead of a y equals. So I'm going to have now, I have an x squared equals 4 minus y. X equals the square root of 4 minus y. So now that's going to go over here, and I have the square root of 4 minus y here. My bounds for the integral come from the picture, but they are now y values. whatever those bounds are in your integral need to match the variable that you are integrating with respect to. So in this case, it was 0, and I knew it was 4 from maybe you were using your graphing calculator. Maybe you just know that that parabola has a y-intercept of 4. All right, and then this is now what I'm going to integrate. I'm going to take that pi on the outside of the integral because it's a constant multiple, so it can be pulled on the outside. And then the square root squared really does go away. In this case, it happened to be kind of simple. And I got pi times the integral from 0 to 4 of 4 minus y dy. So now I'll integrate that. The antiderivative of 4 is 4y minus the antiderivative of y is y squared over 2. Evaluated from 0 to 4, pi times, if I plug in 4, I got 16 minus 16 over 2, minus pi times, if I plugged in 0, I happen to have gotten 0, so I got pi times 16, sorry, minus 8, there we go, that was a 16. There we go, okay, so all that worked for 8 pi units cubed. Ta-da! All right, so now we have the disk method. Great. So now we have the disk method. Let's go through and do the washer method. All right, so one more method for this video. So what about finding volumes of solids of revolution when they have a hollow piece on the inside? I think this picture really kind of shows it all. So instead of doing an entire spiel revolved all the way around, maybe I have it cut off a little bit. And so when I revolve that, you can see from that picture here on the right-hand side, if I revolve it around with a blank spot in the middle, I've created a washer or a flat donut, whichever is your analogy of preference. This is now going to be called the washer method. And I'm going to take that washer and I'm actually going to redraw that exact washer that you see, but so that I'm looking at it head on, so on its side. Now it kind of really does look like a flat donut. And then it's a little bit more obvious. How do I find the area of that cross section? Well, the area of that guy is going to be quite simple. It's the area of the bigger circle minus the area of the smaller circle. So I just used big R and little r. So the area of that washer would be pi times big R squared minus pi times little r squared. All right, that's not so bad. We got this. All right, so that's kind of the general idea. You're still going to add up infinitely many, so it's still going to be an integral. And that's where we got this formula right here. I don't recommend you memorize that formula. I really don't. I don't think that would help you because not every function is called f of x. Sometimes it's called h of x. Sometimes it's g of y. Like, you don't really know the names of the functions. So I think what would be better, rather than memorizing that formula, it's correct. I just think something that would be better would be the integral of pi times big R squared minus pi times little r squared. All right, I just feel like that might help you visualize it a little bit better. So that's how I'm going to try to visualize it. And of course, it might end up being dy, just like that last example. It's very possible. All right. So let's do an example. And in this one, I'll do a visual for you guys as well. So R is the region bounded by y equals 2x squared and y equals 2. And I'm going to find the volume of the solid created when R is revolved about the y-axis. Let's start off by drawing this in 2 dimensions. All right, I'm going to start off with that. I've got y equals 2x squared, which we know looks a little something like that. Here's my y equals 2x squared and y equals 2. We know y equals a number is a horizontal line, and I'm going to revolve this around the y-axis. So I'm going to shade in only half of that region, and I hope you guys can see why, because I'm going to take that entire region and I'm going to now revolve it around the y-axis. So it will already encompass that second region, so I don't need both of them, all right? So when I revolve that all the way around, oh, I think this one has the typo. I'm so sorry. This is going to not be the one that we want to draw. Let's look at the picture. I think that one actually I meant to have you draw it around the x-axis. And let's look at the picture. I did. I'm so sorry. So that was a typo. Let me come back to that. But this picture is correct. I'm going to come back to the picture that I just drew. I promise I will. So what I'm going to do is that region, the solid on the left there in 2 dimensions, and then on the right, I'm actually revolving it around the x-axis, not the y-axis. So you can see that sliver there when I've rotated that little sliver around the x-axis, you can see the washer that it creates. And I think sometimes it's helpful to actually watch it be created there. Let me do that. Okay, there's my little sliver. And if I revolve it around the x-axis, you can see the washer that it creates. And then if I were to do the entire region, you can see this is the object that we're trying to find the volume of. Okay, all right, let's go through and fix that typo. I do apologize. This should have said about the x-axis. I wanted to match that picture I had in CalcPlot 3D. Okay, so I'm actually revolving this around the x-axis. I'll redraw my sliver. There we go. And I am going to do, now it says specifically the whole region. I don't need to do half because I'm not revolving around the y-axis. There we go. So it's that entire region. That's a little bit better. I apologize there. All right, I'm going to take that sliver that I've just drawn right here, and I'm going to revolve that around the x-axis. Hopefully you can see the washer, and it's going to be the same all the way around. You see how some of those washers might be bigger than others. That's what we're trying to find the volume of. Okay, so the volume is going to be the integral. Each one of those slivers that I'm choosing to create those washers are vertical slivers, which means I'm going to need a dx, and I'm going to need a pi times my bigger radius squared minus the pi times my smaller radius squared. That's really what you're thinking. I recommend you write down pi big R squared minus pi r little r squared. It's just more visual so you can see the bigger radius and the smaller radius. So in this case, the bigger radius you can see was that y equals 2. When I did the revolution of that sliver all the way around, y equals 2, the straight line, was on the outside of the washer the whole time. And then y equals 2x squared, the parabola, was on the inside of the washer that whole time. So the outside was the y equals 2. That was my bigger radius. And then the smaller radius was the y equals 2x squared. And then my bounds are going to be where they intersect each other. So I'm going to go ahead and find those intersection points. You might be able to figure that out if you have your graphing calculator. I'm going to just show you how to do that by hand so you always have the tools. 2 equals 2x squared. I just set the 2 equal to each other. So 1 equals x squared. So x equals plus or minus 1. That's where I got the bounds from -1 to 1. Okay, I'm going to simplify this. This becomes the integral from -1 to 1. I'm going to take the pi on the outside because it's in common multiplied by everything, so I can factor it out. And I have 4 minus 4x to the power of 4 dx. All right, we're doing good. We're doing good. And then I'm going to try to find this integral. So then I have pi times 4x minus 4x to the 5th over 5 evaluated from -1 to 1. You might have noticed the symmetry, and then do the 4x minus 4x to the 5 over 5 evaluated from 0 to 1, but just double it. You're allowed to notice that symmetry. That symmetry was straight from the picture because it was symmetric on both halves. You don't have to notice that. If you don't want to, you could have just kept it as the bounds from -1 to 1. But I got 2 pi times, if I plug in 1, I got 4 minus 4 over 5. And if I plugged in 0, I got 0. So I have 2 pi minus 4 fifths. You could think of this, we can do this by hand so you guys can see how to do it. I would make that 4 is the same thing as 20 over 5 minus 4 over 5. Of course, you could use your calculator if you prefer, but that way you have this option here. And I ended up with 16 over 5. So all that worked for 32 pi fifths units cubed because we found a volume. Ta-da! All right, so now we have the 3 main methods that we've learned in this video, all right? And there's plenty of other examples here that you'll be able to see the answers on D2L for, or you can always email me if you want extra help with them. Try to practice those extra examples. Try to practice those extra examples. But the main 3 things that we learned were the slicing method, the disk method, and the washer method. We're all about finding volumes. Step 1 is to draw the picture. Try to visualize what's happening each time before you go through and find the volume. Ta-da! Thanks, guys.